unusual students. And so what we did was we recorded 11 80-minute lectures in the proof-based advanced mathematics courses across 3 universities. And then if a student agreed, we would pay them $10, 10 US dollars, to photograph their notes. Now, in some cases, we photographed an empty page. In one case, we photographed somebody's physics homework. But we for the most part, the students, about half of them agreed to pay the $10, sign the consent form, and let us take copies of their notes. So you can see there's about 200 students in the 11 courses, so this context is probably different than it is in New Zealand, where the lectures are to hundreds of students apiece. And we analyzed the lecture, and then we flagged every time we felt there was some type of informal content. So giving a conceptual explanation was if they gave an informal representation, like a diagram, or made an analogy to earlier content. So comparing splitting fields to polynomials, for instance. Providing a heuristic or a method for how to write a proof. So that was the Cauchy sequence would be an example of that. So here's what you might want to do. By the way, a Cauchy sequences bunching up would be a conceptual explanation for what Cauchy sequences are. Modeling math behavior. So this was saying, well, mathematicians would naturally generalize, or making some type of judgment. This is a good definition, this is a bad definition, that sort of thing. Or then giving an example, that's like 5 is an example of a prime number. And so we looked to see if these ideas we looked at how they appeared in the lecture, then we looked to see if these ideas were present in any form in the students' notes. This is what we found. So conceptual explanations were very common. So these were 80-minute lectures. We saw about 21.2 in the lecture. They were usually expressed orally, usually when they were written as if they were using a diagram. When they were written, more often than not, they appeared in the students' notes. When they were only expressed orally, they usually didn't. We could go down to heuristics. Same story, they weren't quite as prevalent, but when they were presenting problem solving or how to writing proofs, they often gave heuristics about what one do in writing a proof. These were usually expressed orally, not written, and we noticed the same pattern, that if they were written down, the students would write them. If they weren't, they weren't. The modeling mathematical behavior, like this is what mathematicians would naturally do, or this is a good definition. We saw, again, the same pattern. These were almost always just said orally, as you can imagine, but then they very rarely were in students' notes. The examples told a different story, so we weren't predicting this, but actually most examples were written down. We thought they would be oral as well. It's because the mathematicians would then do some type of computations on them. But we got the same trend. When they were written, they more often than not found their way into students' notes. When they were just said orally, they were missed. So what we think is going, so just to say the hypothesis that generalized, we said that lectures weren't formal, informal content was frequently being expressed, and I think that this supports this, that if you add these together, it's more than once every 2 minutes they were expressing what we would convey as informal content. The informal content was usually said orally, not written. Mostly true, with the exception of examples, which actually usually were written. And then oral is not written down. This is about as strong as a result as you're going to get in math education. Now, just for the sake of completeness, that definitions, theorems, and proofs, these were prevalent in lectures, although probably less than you would predict when you say it was a definition, theorem, proof format. There were only 3 proofs for an 80-minute lecture, and part of it's that proofs take a while to present. But these usually were written down, and then they usually did go into the students' notes. So, well, what we think is happening is that mathematicians have a tough job. They have a lot of content that they want to cover, so they write the proofs down, and then they provide the oral commentary. That's the value added to the proofs. After all, the proofs and the definitions are usually in the textbook. Now, what's going on with the students, we think, is that they have to prioritize. Now, what's written on the board has a permanence that oral speech lacks. And one of the things that, if just informally, not from research, is students think lectures go very, very fast. They have a lot of difficulty keeping up. So what students are often doing during the lectures is just trying their best to copy down what they could from the board. So I don't think anybody's doing anything wrong, but this is meshing very poorly. That the things that mathematicians think are most important and they're trying to convey, and this is their masterpiece in the lectures, are being missed by the students because they're just trying to keep up and focus what's on the board. Now, this screams for some type of active learning approach where the students aren't just passively copying, but are being made or encouraged, or at least the opportunity to think. Mathematicians, to their credit, are aware of this, and so I will not go over this other than to show this slide and to say you could look at the reference to see the methods. But we analyzed the same data set, and we found that there were 56 questions where students were invited to make a mathematical contribution per 80-minute lecture. So this isn't of the form like, how are you doing today? You know, it's what's the definition of this? But what we found is that, at least from a math ed perspective, this didn't lead to very deep engagement in the material. 2/3 of the questions were closed form to like state the Cauchy's theorem, like we saw earlier in the slide, or what's the next step in the proof. Almost all the questions had very limited wait time, 3 seconds or less. And there was only one question per lecture on average that involved something beyond the next step or filling in a definition or a missing fact with 5 seconds of wait time. So if you're not giving students 5 seconds of wait time, you're probably not asking a question that involves a very deep involvement with the material. And so there were questions there to try to invite students, but there's probably room to do something further. So what could we do? Well, can math education research help? I hope it could. So what we've done in the US is we've designed inquiry-based curriculum that radically transforms the way that we teach. So Ed Dubinsky and his colleagues developed an approach to teaching abstract algebra that involves having students program in a new specialized computer language called Isotope. And the idea is by programming how to compute a coset into the computer, you would kind of have the process in your mind and you could reflect upon it. They've written a textbook on it. They've developed a lot of workshops to try to get teachers to use it, as well as reports of its efficacy. And it seems to do some things very well, but there was a survey by my colleagues where they interviewed 131 mathematicians who recently taught an abstract algebra course. One was using Dubinsky's curricula. So he developed a good curricula, but it's just not being used. I could tell a similar story with my previous collaborator, Sean Larson. He developed this very different curriculum to teach abstract algebra. I encourage you to look at it, but it involves about looking at reflections of common objects like triangles and so on, and developing the symmetries of them, and then developing the group axioms and the group rules, and wound up having the students reinvent some impressive mathematics, quotient groups, isomorphisms. None of this is trivial. And he also was interested in scalability. So he really did try to have mathematicians outside of his group use the materials to see what happened. He developed a website to provide assistance. He developed all these wonderful resources. And same result. One of the 131 mathematicians from Johnson's study was using that. In fact, only 5 of the mathematicians said they were really using math education in a serious way at all, that they more talked to their colleagues to find this. So, well, what's going on here? I think it's that in the US, research and undergraduate math education, as we call it in my country, have this paradigm that we identify a problem, students weren't developing a good understanding of groups and quotient groups and all that. Then we work hard to find best practices in the curriculum to fix it. Then we try to persuade mathematicians to use it through research reports and articles. Then we provide support and training so they could use the curricula effectively, because it's not always so easy. And as you can see, this model doesn't work. We get to step 2 and we never make it past that. Now, from my perspective, there's a lesson from the K through 12 mathematics that math educators in my country haven't internalized yet. So Math teachers aren't free to teach however they like in either the K through 12 settings or the university. They have obligations, and they have obligations to their institutions, they have obligations to the discipline, and they have obligations to their students. And in many cases, these are perceived obligations that maybe they won't be fired if they don't cover the first isomorphism theorem, but they feel the need to do it. And a perceived obligation is an obligation nonetheless. So it's common that we blame teachers in the K through 12 curricula for not using what we consider best practices. And I like the quote from Herbst and Chazen. We say they suffer from a lack of knowledge or a paucity of vision. But Herbst and Chazen say, actually, they have, it might be the case that they have constraints and obligations that we're not recognizing. So we showed these results to that we had to mathematicians and said, well, these are common teaching practices that we've observed. What do you make of these? And then from their responses, we tried to infer what their obligations were. And I've written the obligations there, and you could see that the curriculum that I described really aren't meeting these. So neither curriculum covered the first isomorphism theorem, and many algebraists say an algebra course without the first isomorphism theorem is no algebra course at all. Preparing future mathematicians for graduate school. Mathematicians, I don't mean to generalize, but many of them really do care about the top 10% of the class. Math educators really do care about the bottom 50% of the class. And by not saying how the top 10% could do, they might feel that we're not meeting their needs. Precision in language is a big thing, and an efficiency in teaching preparation. So Dubinsky's curriculum requires mathematicians to learn a new computer programming language, which is a big ask. Now, they also did say that they wanted to maintain student engagement and develop a good understanding in all the students. That was one of their obligations, but it was only one of them. So my interpretation is that when we are upset that bemoan the fact that they don't use our curriculum, you can imagine, suppose that there's some people that are eating too much fast food at lunchtime when we want to make them healthier. So we go, all right, well, best practices are to spend an enormous grocery bill and then to spend an hour preparing your lunch every night before you go to work. And then they don't do that and they continue getting the fast food. And we go, well, I guess they just don't care about their health. It might be the case that we're not putting them in a situation where they could, where they could actually do this and it meets their budget critique and their time. So I was reminded of a nice paper that Laura Alcock wrote where she interviewed mathematicians. And in the introduction of the paper, she had 3 principles about dealing with mathematicians. We should have collaborations on good faith and respect. We need our interventions to meet mathematicians' needs, not just their own. And finally, mathematicians have expertise that we lack. They've frequently been teaching for 20 or 30 years and know about what might work and what might not, and where students might get stuck, and we should capitalize on that knowledge as well. So if we look at the model here, where are the mathematicians? Well, the mathematicians, we want them to use our curriculum and we want to support them when they are, but do we have them involved in identifying the problem and what their needs are? Do we use their resources to fix it? And not everybody is like this in the US, and I think that but sometimes you hear at conferences, although not written reports, a frustration with the mathematicians about them not getting it. That's not really very respectful either. So if I sound like that I'm not supportive of Dubinsky's work and Larson's work, then I've given the wrong impression. I actually am a big fan of both the curriculum, the APOS framework about which Dubinsky used is kind of in my mind, and I can't unsee mathematical concepts as well of it. I encourage Sean Larson to do a special issue of JMB because I thought the work was spectacular. We learned an awful lot about the way that students think and ways that we could help students develop understanding. But I hope my colleagues don't think this is too harsh. What they thought they were doing applied research, but what I'm showing you is that they actually did basic research. They developed a good understanding about the way that students could learn in a very interesting and rich way, but they're not changing the way that mathematics is taught. So what's the alternative? Well, I don't know, but I have started a project, and I'm going to share some preliminary results on this. Tanya, how am I doing on time?
Great. 2:30.
2:30, okay, 10 minutes or so? Okay, very good. So 10 or 15 minutes. So this is a collaboration, and Lisa Carbone is a eminent algebraist and a mathematician very interested in active learning at Rutgers University. And Tim Fukawa Conley is a frequent co-author of mine, a math educator at Temple. And Estrella Johnson's a math educator at Virginia Tech. And we obligatory thanks to the National Science Foundation who funded this work. And what we did is we developed a collaborative collective with 4 mathematicians who were teaching a proof-based linear algebra course. So at the university in question, Rutgers, they have a course called 250, which is the calculational one where you find out how to compute inverses and find eigenvalues and all that, and the RN case. And then the university math students take a proof-based course that's more abstract, the more abstract version of it. And what we wanted to do was introduce some active learning strategies into the classroom. We wanted to do it a little more gentle than kind of completely upend the course, but to see what we could do. Clicker questions type things for people who know that literature. And so we set it up so we would meet weekly, and we would, us math educators, the research team would propose strategies, and the mathematicians had the right to reject them. The only rule that we had is if they rejected them, they had to supply a reason. We wouldn't argue against the reason. We would just want to know what the reason was so we could work around it. If a strategy was agreed upon, we would work together on its implementation. In some cases, the mathematicians were happy to let us generate the questions, but in some cases, they would have some ideas themselves. And then we would observe how it was implemented, and they would debrief on the implementation in the next meeting. So I'll report on the first cycle. Due to the, not to be ungrateful to my funding agency, they told us we could start on September 1st, but then due to some fiscal year stuff, we didn't get the funding till October 1st, so we only had 6 meetings. We were hoping to have about 14. So here's what we found. When we analyzed the data, when mathematicians gave us reasons for rejecting our suggestions, we would try to see if there were obligations at play. There weren't always. Sometimes they just thought these wouldn't work, but there often were. We can't do this because of some other constraint. We had an initial trajectory for the activities where it would be more and more student-centered. The trajectory wasn't very good, but afterwards we would try to then go back and rethink and say, how are we thinking about this wrong so we could develop a better trajectory for next term? Then after analyzing all our data, we went back and met with each of the three of the 4 mathematicians individually. One was in China and unavailable to meet. And we said, this is what we thought you were saying. These were our conclusions. Do you agree with that? And what do you think? In qualitative research, this is known as member checking. And we do this to increase the trustworthiness and the validity of our study. But you also get good data from that. Often when they expand, you get a fuller picture of what they were thinking. So here's what we found. We really didn't have our finger, even despite I had done a lot of research on mathematicians thinking about teaching. And so we went in we'll start with exit tickets. Exit tickets are something in the elementary and secondary math, so you give a lecture or some activity, and you give students some type of question on what you said, and they provide a written response. That provides a window into how they interpreted your lesson. And we thought this had 3 virtues. It takes almost no time. You just pose the question at the end of class and you collect the paper, so you still have time to lecture. Mathematicians would be surprised at what students did or didn't learn from their lectures, that maybe they were less effective in conveying what they wanted. And then finally, they would see the value of having student engagement and seeing students thinking. None of these things are true. First, the mathematicians didn't expect students to do well on the exit ticket because they thought it took time to review the notes. They're like, no, of course they didn't understand the lecture fully after I gave it. Take some type of reflection. They also said, we already know it's useful to look at students thinking, and indeed, all of them had some activity that they describe. Well, I did this. It's just, they thought student engagement and thinking was good. It's just that they didn't have the time to do it. So there were some very cool activities that they said they did. So one of them, which I quite liked, was this was a proof-based linear algebra. They said we took all linear combinations of a constant times sine of x plus a, where it could be NEA. So that's the vector space. what's the dimension? The dimension actually is 2, which surprised me. I would have thought for sure it was infinite, but he goes, this activity takes 20 minutes in the class. The students forgot the sign addition formulas. It's a really good activity in getting students to think, but I could only do this a couple times a term. And then finally, we thought, if nothing else, the exit tickets would be quick. No. So they all complained. They said, well, it took too long. We're like, what do you mean it took too long? But then we looked at the field notes. The next day, all the mathematicians would spend 5 or 10 minutes going over the exit ticket questions. They couldn't leave a question unanswered. So we really didn't have a sense of what was going on. But gradually, we came to understand that there were 3 obligations that the mathematicians had. Content coverage, abstraction, and complete answers to every question that was asked. Now, I don't want to spend a lot of time on content coverage. We all know, I think intuitively, that mathematicians want to understand content. I just want to emphasize the strength with which everybody in the study had this obligation. I like the one quote, my biggest adversary in classroom when I'm teaching is the clock on the wall. This was said repeatedly. Now, the abstraction was interesting. So the idea is this, that the 250 course is when you do the computations on Rn, matrices with the real numbers. Now, the 350 course, we want students to see, we desperately need to see that vector spaces are much more than this. So actually including examples from Rn, they thought was defeating. We thought, usually in math education, the idea is you start with what students know as an example and then build from that. This is a common recommendation. They really didn't like this because this is reinforcing to the students that matrices are Rn, where they really wanted them to think about complex numbers or function spaces. And this did not play well with the content coverage or being quick because all the examples that we could give them required time for students to process this. So one of the things like a linear transformation was differentiation, and we said, suppose that you had an infinitely differentiable function space. You would need that for the closure, and then they're like, oh, geez, well, once you put infinitely differentiable, you're going to lose half the students in the room to try to process this. So this was a constraint that was hard to manage. And as we said, the complete answers to every question, we were very surprised by this. We thought that, okay, then you say, well, actually, the answer is this, and go on with your lesson. No, all of them gave a response like this. In mathematics, it's an obligation to the discipline. We're constantly trying to keep a very clear boundary between what we know and what we don't. So the idea that you could give a hand-wavy answer is something that they thought would do more harm than good. Now, we could fight these obligations, but that wouldn't really be in the spirit of what we were trying to do. What we wanted to do was find a way to work around them. Now, just to give you a sense about the way things went, there were a lot of negotiations that went like this. So here, Lisa was the mathematician. She goes, well, what if you introduce a question and go on with the lesson and then come back to it? And then the mathematicians were like, no, students can't think about 2 things at once. I actually agree with the mathematician on this point. They can't even think about the oral content and what's written on the boards. They're not going to be processing a question in the meantime. So then Lisa goes on and goes, well, what if you give the answer to the question as a proof that they can watch later? And they go, no, they're not going to do this. So there's a give and take there. We would pose suggestions, but we had to accept if the answer was no. What we ultimately landed on was this, that students would be asked to give like voting questions. They wouldn't have to give complete questions with long explanations, but like just something where it was either multiple choice or even yes and no. We integrated the questions so it was going to be covered. So what example were you going to go over? Okay, we'll ask a question about this example. Yes, they'd have to wrestle with it, but they were going to have to wrestle with it anyway because that's the example you're going to provide. Here's the theorem. Do you think the theorem is true, or do you think the negation of the theorem is true, or do you think something implied by the theorem is true? Students get a minute to think about it. They give a vote. Well, you were going to cover the theorem anyway and give them a proper answer. Or one of the things that I quite enjoyed was to go through the proofs, and I would look at the steps that would be conceptually challenging and ask them, do you think that this inference would hold to the students? Yes, no, always, sometimes, never. Now, this could be quite hard, but look, you were going to do this in the proof. If the students actually didn't know the inference, you would have had to address this in the proof anyway. So we were trying to set these things up so they wouldn't take time, but they also would go with the flow of the lecture, so the mathematicians didn't have to do a 5-minute detour to explain. And it worked. They liked them. There was one point here that I didn't appreciate coming in that I learned from the study, is that giving mathematicians some amount of flexibility was really helpful for doing this. So the way they all had different beliefs and needs about the way that these things should go. So one mathematician created panels, so he made little colored sheets, and that's what the students were voting on. He did not want to use hands because he was afraid that students wouldn't really think. They would just look at what the other students were doing, the smartest kids in the room, the strongest personalities. And he did not want to use technology because he thought that would be too big of a deal for the students and it would be too big of a production. Mathematician 2 said, hands is simplest and quickest, that's what I'm going to do. If you could give me the technology, I would prefer that. And the third mathematician said, I would have the students write it down and then hand it in between class. And he would actually use this not to see what they were thinking, but to go over to individual students and talk with them to get their ideas. So there were 3 different ways that these ideas were being implemented. We would also give them kind of a bank of questions, and they would use the ones that resonated with them. So they actually, although they were all teaching linear algebra, had different goals for the course. So M3 really was interested in applications. So we talk about radio frequencies and stuff that to be honest, I didn't fully understand. The M2 is really interested in kind of the abstraction, using this to prove other mathematical theorems. And M1 really wanted students to be engaged in the thinking where the content was somewhat secondary, although we still felt the need to cover the content because that was part of the contract. So we had a method that was flexible where the mathematicians could use it to meet their needs. Now, was it successful? Well, I'm a little reluctant here that I don't want to be a propagandist and say we did the most wonderful thing in the world. So take this with a grain of salt. At the end of the day, we spent 6 weeks finding a way to get students, mathematicians to use think, pair, share questions in their lecture. I mean, I'm not expecting a Nobel Prize for this work. But one of the things was, when you were part of it, we were all very happy with the result when it came out of it. We really felt that we were understanding the thinking and changing mathematicians' practice in a small way. The mathematicians felt that they were listened to and that they had a method that they could do to change their practice and get students thinking, albeit, I think, to them in a big way. And so all of them said that they felt afterwards that the method was being used. In the member checking interviews, we asked them are you still using these techniques? 2 of the 3 said they were in the courses they were teaching, and the third said, I couldn't because I was teaching the 250, which was calculation, but next time I teach linear algebra, I intend to use these. And we got nice comments like this, that what we liked is that you actually listened to us and we were able to do this. So if you look at the bottom section, my main worry about active learning is always the time constraint. When we work with you, you listen to what we are talking about and then did these things that we see. I think now the format works. And more and more stuff about the guy telling us how wonderful we are. But I like this. In the beginning, I'd have to say that I was a little bit skeptical about whether this activity will be useful. But now after this semester, I think that it seems to be much, much more effective than I thought. And I wanted to let you know this because you were the person who actually did the study. So what did we learn from this? Again, this was just kind of the pilot, and we're going to try to do better next term. That, well, to mathematicians, time is the ultimate currency in the classroom. Now, we all sort of know this, but I think that we really need to take this seriously. If you want to go and sell a product to me or a business in the US dollars is going to be my ultimate currency. Now, you could try to convince me that the mighty US dollar isn't the best thing to focus on, and I should focus on fulfillment and this and that. That's only going to get you so far with so many people. We have to respect time if we're going to do this. Now, the metaphor that we learned is that that mathematicians have obligations, and these obligations require time to meet. So we weren't aware of all the obligations, and they increased the cost of our activity. So if the mathematicians are going to do something, it needs to be worth it, but the cost is higher than we realized because of the obligations that mathematicians had. But on a happy note, by attending to the obligations and working together, we were able to achieve a solution that met all of our needs. So, to wrap up, so I said that lectures are ineffective, but I tried to give a good reason for this instead of blaming people. There's probably multiple ways to address this, but to the mathematicians in the room, I often say when they're trying to plan their lesson, like, well, what's the right example? What's the right metaphor? What's the right gesture I could do? I'm all for good explanations and good metaphors and good examples. This probably isn't going to be getting at the root of the problem, though. The root of the problem is you need to get the students to attend to what you're saying orally, or alternatively to write down the most important points. If you're not doing that, it's probably going to be missed, and that's just the way that it is. To my math education colleagues, I think the innovative curricula really taught us a lot about the thinking and learning, and I really don't want to say that I'm kind of attacking it, but it's not being used, and I think that this is in part, and this is what Michelle Artigue said in the opening quote, we're not considering the obligations of the mathematicians. In the United States, one of the things in the room community now is to try to change department culture. So, well, the mathematicians have these obligations, let's change the culture so they don't. Maybe that'll work. It's not the approach that I would favor. I don't want to discourage it. I am always let 1,000 flowers bloom. Let's try to do things all possible ways and see what works best. But I think that trying to get mathematicians to not care about the things they currently care about, I think there's diminishing returns. So in terms of our study, obligations add costs in terms of the time to any student-centered activity that's being used, but genuine collaboration can lead to positive change in undergraduate teaching practice. Thanks.
I'm a mathematician, so that affects what I'm going to say. Do you think about the difference between, so I guess what I might call a cheap and cheerful solution versus what I see a lot from mathematics people, which is we'll go and develop this new framework to do this and do this and that. Because what I took from your first little bit about the lectures and notes is write things down. So this on the board, so the students will write them down in their notes. And that's something that many mathematicians know. What is there something in studies in mathematics that you're aware of that work along those kind of lines around what can we do to fix small problems with cheap solutions rather than launching into new theoretical framework?
Good question, Lisa. I think the answer is no. I've written a book chapter advertising, I think I call them like non-invasive techniques. Cheap solutions is what I was saying as well. So Tanya and I were actually talking about this over lunch. It's quite curious that in physics education, there's a peer instruction where it's, just trying to find a way to make clicker or think, pair, share questions, put them into the lecture to engage students. And for whatever reason, in undergraduate mathematics education research, this is a route that hasn't been taken. It's been very under-researched. In a recent paper, Paola Iannone used partial notes. So the idea is that you would be teaching, I don't remember the course, real analysis say, where you would actually have students write in the oral part of the lecture that's important to focus their attention on that. Here, you're given the proof, add the warrant for why this step follows or the heuristic that's being used. And so this is one study, and I'm not aware of many others, if any. And what she found in that study is students did actually write down the most important parts, which partial notes does. Epistemologically, they didn't think that they were that important. They still thought it was the definition, theorem, proofs that they should have been focusing on. There wasn't any measure about whether they actually learned more from the lectures that they were doing. I hesitate to bust Paula's chops about that because I didn't provide any evidence that the students learned more either. So in my opinion, I think that this is a serious deficiency in our field, that in math education, educational psychology has produced a lot of work about how students could learn more from lectures. And one of the routes that we could be taking is to try to incorporate those ideas into math education lectures. Sorry for the meandering response. I'm surprised I forgot this. There was a self-explanation study where if you had students, it's not lecture-based, but to learn more from the proofs, if you had students generate a self-explanation for after each step in the proof, their comprehension of the proof goes up quite a bit than if they just read it and they're left to their own devices or observe it in a lecture. So I think that there's a lot of room there, and we haven't taken it. I have theories for why we didn't do that right, but there's a bifurcation between the math ed in educational psychology and math ed in what we consider the mainstream math education, or at least the room movement. And I think that theoretical differences aside, a rapprochement between the two fields would be mutually beneficial.
Yari?
How did the students respond to the change?
Here,
Yeah.
you know, honestly, I haven't the foggiest, and we really should get some data on this next term. We were working so hard on just getting the mathematicians to change. We absolutely should see if the students enjoy the changes. And also, one voice that we haven't heard from, we have math educators, we have mathematicians. Students should also get some say in what would be good teaching practices.
Thank you very much for your talk. What do you see as the duty for, what are the responsibilities of the students? Because coming into undergraduate schools, I think undergraduate level math, I don't think students are really taught how to learn or how to engage with that, because they're coming from the, from secondary education. It's very, very different the way that's structured. What do you see students' role within this change that you want to bring about?
Now that is a very good question that we don't really think about what students ought to be doing outside of class. So one belief that mathematicians have, at the risk of overgeneralizing, is I only have 45 contact hours a semester. It takes much more than 45 hours to develop a rich understanding of proof-based linear algebra. They should be working and studying on their own, but it's sort of left as an individual effort into what the students should be doing. So I think that, sorry to duck a question with, this would be a great topic for future research, but it really would. What are students doing outside of class, and how can we help them learn how to learn, so to speak? As for what that is, I think I would wind up just saying the same thing that as any practicing mathematician or kind of like a layman math educator, that they should be trying to look over the proofs to be sure they understand each step, to be sure that they can generalize it. I guess I could give a slightly better answer that my colleagues and I have developed proof comprehension assessments. And so we did say that the obvious thing, that you should know what each statement in the proof means, you should know why each statement follows, and you should know why the assumptions and the conclusions, how they fit into the proof framework. But we also said, can you give a summary of the proof, a condensed summary about the main ideas? Can you apply the proof of a general theorem to a specific example? And can you generalize the method of a proof to prove a similar type of theorem, or see where it breaks down and why it doesn't work? So I guess I would advocate that these things aren't at all obvious to the students, and we could say when you're reading a proof, these are the type of things that you should be attending to.
Okay, I'll ask the last question then, or maybe a comment rather. I really appreciated your positioning, the rationale for this talk, as kind of a standoff between the two camps, the math education researchers and mathematicians. However, I would have said something different, and from our experience here on the ground, a lot of rejection that was coming out from mathematicians were warranted, because originally the mathematics education researchers that came up with this revolutionary new modes of delivery of lectures, those suggestions were actually not supported by educational psychology, but they didn't know about it. And for example, here we had a whole semester trial of basically an inquiry-based stream of one of our large service courses that didn't quite work. And I would say that mathematicians were rejecting those sort of invitations to engage, not because they had necessarily the obligations and they was just stubborn, but the obligations that you call them obligations, they were just coming from the perception of they could smell the rat. They could smell the rat, and they knew this is something fundamentally wrong. There's no way our students will learn this way. But they couldn't communicate that clearly, and that's where the divide appeared. And so what you're trying to do, you're trying to do things properly. You're trying to use the latest cognitive science findings and actually bring something to mathematicians that doesn't smell bad anymore. And so, thank you.
Okay. I'll play ball with this. So I'll be frank about this. You're saying we're trying to sell them a bucket full of shit, and they don't want it. I can respond to that a little more diplomatically. So one thing that I would agree with, and I hope most of my colleagues would agree with, students are going to learn more from a great lecture than a poor inquiry-based classroom. And students would learn more from a great inquiry-based classroom than a poor lecture. So I do not like putting these things in opposition. And I also think when I teach my classes, I lecture, but I try not to talk for more than 10 minutes in a row before I give an activity. And I also try to put in inquiry-based activities.
But that's not inquiry-based learning.
Yeah.
You provide the explanations, and it's not inquiry-based learning. Yeah. What was smelling bad is the explanations are minimized.
Yeah, I mean, I think if you go too far in any direction, or also even if you have a balance, but you just do it very poorly, if you have stupid collaborative activities, nobody's going to learn from them. And so, I mean, the curriculum that I was talking about, I think that they were well-developed curriculum that were achieving their goals. Now, there is always the issue about what the goals are, and one of the things that I've noticed is that for both Dubinsky and Larson's curriculum, they didn't give a post-test where students were asked to prove stuff. You know what mathematicians want students to be able to do? Prove stuff about their content. So if you radically alter the goals, you're changing the problem that mathematicians ask you to solve. So I would say that we could be guilty of that, but I'm skeptical. I don't like trying to say, well, does inquiry-based work better, or does